This is the first lecture of Unit 4 and we'll try to cover a brief introduction to basic concepts involved in working of general AC motors. Then we will learn about hysteresis motor. In this unit we will be studying about the special motors, more specifically hysteresis motor, reluctance motor, stepper motor, universal motor, further followed by topics dedicated to industrial power supply, namely auto transformer, welding transformer, tariff system, and power factor improvement. We already learned that electrical machines are broadly classified into static machines and dynamic machines, which are further classified as AC and DC. DC motors were already taught in Unit 2, while a part of AC motors is in Unit 3, and some of them in this unit. AC motors are further categorized as asynchronous and synchronous motors. Then you have further classification of asynchronous as induction type and commutator type, while synchronous as DC excited and non-excited type. Then they are further classified into more types. We will only focus on motors in this unit, namely hysteresis, reluctance, and stepper motor on synchronous branch and universal motor on asynchronous side. So there is one more classification as permanent magnet type of non-excited synchronous motor, and since it's not the part of syllabus and we'll not be discussing about it. One thing more that needs to be discussed here is, while most references write these motors to be single phase only, the hysteresis and reluctance motors to be single phase, there are few references that say they exist in polyphase as well. In fact, if you look into the name of these motors, the name comes from the way they work. That is, it is the rotor design which makes the operation different for these motors. While the purpose of stator winding is solely to produce a rotating magnetic field, under the influence of which the rotor has to rotate. Thus, it is not important that this rotating field is achieved by single phase or two phase or three phase. Nevertheless, one thing that can be argued upon here is that we switch to higher phases when larger load is to be handled. While these motors are designed to handle fractional or subfractional load, which can easily be achieved by incorporating single phase windings on the stator. Moreover, there are stepper motors designed to operate on DC supply. So such motors come under the classification of DC machines and not in AC. Asynchronous motors are commonly used in tasks where precise control of rotational speed is required, or where the maximum value of power, efficiency, etc. is required. One thing to note is there are several other types of special motors, and each with different benefits. And so they are not the part of the syllabus of this subject, and hence will not be discussed. Now we first introduce the basic concept of rotating magnetic field and how it makes the rotor rotate before diving into the main content of the syllabus. So this is just a quick recap of AC motor operation. Well, the essence of working of AC motor is based on rotating magnetic field, which can be understood by this given example. So the figure here shows two outer magnets and an inner magnet. In fact, unipolar magnets do not exist, so you will be always having two poles, one north and one south. So just for the sake of things and making things easier, we show single poles. Now what happens when the outer magnet are rotated? So suppose we rotate the outer magnets in clockwise direction. So once the outer magnet are rotated, the inner bar will also experience torque in the same direction, forcing it to rotate in the same in that direction in this manner. On further rotating, the outer magnet will make the inner magnet to experience more torque and will try to follow the same track as that of outer magnet. And since we are talking about synchronous machines, so if the rotor rotates along with the rotating field, it qualifies as synchronous motor. Now shown over here is a demonstration to understand how rotor actually works under the influence of a rotating magnetic field. So if you look into this figure, so note that I just told you that unipolar poles do not exist. So the figure does not show unipolar magnet, but in fact it must be having two poles. Now, once the needle is placed, it experiences the torque in the direction of rotating magnetic field, and thus starts rotating in the same direction, with the same field as that of rotating magnetic field. So the needle gets oriented exactly along the external magnetic field. But this needle is not going to rotate your load. The idea behind may be that simple, but the construction of motor is not. In fact, it is the magnetic field under the influence of which the rotor operates. So rotating outer magnet is like rotating the magnetic field. Furthermore, the idea of making a motor is to obtain mechanical rotation as output from input fed in electrical form. Thus, several designs of stator and AC motor were introduced, and you already have studied them in first year, which, when energized by electric current, produces a rotating magnetic field. For example, for a single-phase motor, we have split phase, shaded pole, capacitor start, capacitor run. So these are something that you have already studied during first year. So shown over here in this figure is a shaded pole type of motor. In fact, it's a stator without rotor. So these all type of motors produce rotating magnetic field. So the figure shown over here is a shaded pole type, which when energized produces a rotating magnetic field like this, which rotates at a speed of ns equal to 120 f by p, where f is frequency and p is the number of poles. For instance, the number of poles in this figure are 2, so p will be taken as 2, and f is the frequency of the supply given to the stator. So if it is going to be 50 Hz, then the synchronous speed that will be generated here is 120 times the frequency equal to 50 divided by 2 poles. And since that you have already studied about rotating magnetic field in first year, notice that here the rotating field is clockwise. To make the field rotate anti-clockwise, the shaded band will be provided on the left side of the pole instead of right. In fact, the field is confined inside the stator periphery except for the stray magnetic field that leaves the stator. So again, for if you have a 4-pole machine, the pattern of field looks something like this. Now here is an illustration that shows how actually rotating field are produced by the stator. So observe again here a correction. The field should have been confined inside the stator frame. Moreover, the field must be present throughout the motor length. Now we talk about hysteresis motor. So as the name suggests, in this type of motor, the mechanical torque required to rotate the rotor is developed by utilizing the phenomena of hysteresis. And these motors are available in fractional horsepower up to 200 watts. So fractional horsepower means that the wattage, the power rating of such motors should be less than 746 watt. These type of motors are self-starting, they have constant torque and operate without noise. The stator windings are similar to induction motor and develop rotating magnetic field when energized. While the rotor is a smooth cylinder and have no projected poles, so there are no teeth, it has no laminations and no DC excitation windings are provided on the rotor. The rotor is made of rings or hollow cylinder of magnetic material, which are drawn over a non-magnetic material mounted on a shaft. So in this figure on the left side shows the cross-sectional view of the rotor, and the outer circle is the ring or hollow cylinder which is made up of magnetic materials. The example of these magnetic material is hard steel, chrome, cobalt, and nickel, rare earth. So any one of these material will be used for making this outer periphery of the rotor. Then the outer periphery of this rotor is drawn over the non-magnetic material, the example of which is brass. The magnetic material employed in rotor should have a high degree of hysteresis, having larger retentivity. The reason is that larger retentivity allows to develop large hysteresis torque. So here now I presume that you are already aware of hysteresis loop and terms associated with it. Now the first figure compares the hysteresis loop of soft and hard material, which shows a clear demarcation in the type of magnet they will form. The second figure compares the hysteresis loop of hard material and a strong magnet called as alnico. So this material is an alloy. It's an alloy of aluminium, nickel and cobalt. While the third figure compares the loop of alnico and a rare earth magnet. So if you look at this comparison, so the hard steel, the hysteresis loop corresponding to hard material, which is quite larger than the soft material, is still smaller than alnico. So the alnico has a larger hysteresis loop compared to hard steel. Well, if you see the third figure, now it shows that alnico compared to a rare earth magnet, selenium cobalt, is comparatively small. So you can think of the second figure to be a magnified form of third. Now here shows some demagnetization curves of magnets. So one of which is the ceramic one, which has the lowest. Here are some demagnetization curve of different magnetic material varying from ceramic magnet to rare earth magnet. So because of being cheap, ceramic magnets are oftenly seen around, while neodymium iron, a rare earth magnet, has the largest retentivity and coercivity values. So if you look in this figure, you will see that the ceramic has the smallest demagnetization curve compared to all other, and larger to this is followed by alnico. So if you see at the vertical axis, which is flux density, while on the y-axis is the coercivity. So alnico has higher retentivity than ceramic and even higher than samarium cobalt. Then samarium cobalt compared to alnico has a larger hysteresis loop, and while the most strongest of all, neodymium iron, has the largest hysteresis loop. So this figure only shows a part of hysteresis loop. It's not a complete hysteresis, but the hysteresis loop can be inferred by looking into these figures. Now let us understand the working of hysteresis motor. So let me explain this point to point. So in a hysteresis motor, the first task is that the stator is energized to produce rotating magnetic field. Then the rotating field magnetizes the rotor, producing or inducing poles in it. These induced poles in rotor gets attracted towards the rotating field, thus experiencing hysteresis torque, causing it to rotate. Now, there's a remark that hysteresis torque can only exist if there is a lag between the stator field and the rotor field. So you will come to understand this in the later figures. So first of all, you will need a stator capable of producing a rotating magnetic field. For example, this shredded pole type that we have already seen before. Then the next task is to replace the rotor of this motor by the hysteresis rotor. In order to understand the hysteresis torque, let us just have a quick recap of hysteresis loop that you studied in your first year. Rotor can be considered to be consisting of small elements made up of magnetic material like this. If you remind the experiment for obtaining hysteresis loop, here instead of winding coil around the specimen for providing magnetic field intensity, we have shown external permanent magnets. So once the element is posed to the external field, the magnetic dipoles align in one direction. And when the field is removed, some of the magnetic dipole remain aligned, making it a permanent magnet with a residual flux. Material that forms strong magnet, such as rare earth magnet, will have this value quite high. Now, if the external field is reversed, it causes a reversal of the magnetic dipole of the elemental bar. Further, if the external field is now removed, the element bar gets magnetized again, but with reverse polarities as shown. Once again the external field is reversed, the poles of element also reverses. Now, using this knowledge, when the rotating magnetic field traverses along the rotor periphery, which is initially unmagnetized, it causes the rotor to develop residual flux, or in other words, magnetizes it. So during a half cycle of rotating field, half of the rotor periphery becomes north, while remaining half becomes south. These induced poles then experience attraction towards the rotating field. When the rotating field moves further, it causes change in the polarities of rotor. This phenomena allows rotor to experience continuous torque. Notice that once the rotor achieves synchronous speed, then rotating field no more sweeps the rotor, and hence polarities of rotor will not change, and the rotor gets locked with rotating field. Now, in addition to hysteresis torque, induction torque due to eddy current are developed, which aid in rotating the rotor until synchronous speed is achieved. Once the rotor reaches the synchronous speed, the magnetized rotor poles lock with the stator field and the motor operates as a synchronous machine. The working of induction torque can be explained by the example of eddy current backing in permanent magnet, moving coil type of instruments, or induction type of energy meters that you studied. Since these are the examples you are familiar with as you studied them in first year. Just as the torque due to eddy currents is exerted on the moving part of PMMC or energy meter called the damping torque, this torque is produced in such a manner so as to oppose the relative motion between the magnetic field and the moving part, thus restraining the relative motion. While in PMMC instrument or energy meter, the magnetic field is stationary and it forces the moving part to remain stationary. In hysteresis motor, the magnetic field is rotating, and this forces the rotor to move such that the relative motion between them reduces, which is possible only when the rotor rotates in the direction of rotating magnetic field. Now, while the machine runs at synchronous speed, no relative motion exists between the rotating field and the rotor. That is, no sweeping takes place. Thus, torque due to eddy current vanishes while the hysteresis torque remains. So this can be seen in the torque versus speed curve at the bottom left. Here the induction torque is shown by shaded region, which gradually decreases with increase in speed of motor, whereas hysteresis torque irrespective of speed is constant throughout. Now the hysteresis torque is given by the expression equal to phi s multiplied by phi r into sine delta, where phi s is the flux produced by stator, while phi r is the rotor flux, and delta is the angle between the rotor flux and the stator flux at synchronous speed. This angle is called as lag angle. The value of stator flux phi s depends on the magnitude of stator current, while rotor flux phi r is decided by the retentivity of material employed, and the lag angle delta has a relation with the hysteresis loop. So delta will be larger if the hysteresis loop is large. So the same thing that I just explained. So if lag angle delta is more, hysteresis torque will be large. Now we will try to derive the expression for torque related to the hysteresis loss. So since the hysteresis losses are produced in the rotor until the rotor reaches the synchronous speed, this is because hysteresis. It is because the hysteresis loop will be observed when the stator sweeps the rotor. If the sweeping stops, which is possible only at synchronous speed, then you will no more get hysteresis loops formed in the rotor. These losses dissipated in the form of heat are proportional to the area of hysteresis loop of magnetic material used in rotor and the speed of rotating field with respect to rotor. So this is clear from the point that hysteresis losses depend upon the size of the loop. So if you have a larger loop, then losses will be more, and also on the times that loop is formed in the rotor while sweeping. So if the frequency of formation of hysteresis loop or the completion of that cycle is more, then losses will be more. So now we can write the energy dissipated in the rotor per minute as N times EH, where EH is the hysteresis loss in one cycle of hysteresis loop. And there is a remark that energy loss during one revolution of rotating field with respect to rotor. While N is the number of revolution of stator field with respect to rotor, which gradually decreases to 0 as the rotor reaches synchronous speed. So notice that N is not synchronous speed, or N is not the speed of rotor. Rather, it is the relative speed of rotor and stator field. So once your rotor reaches the synchronous speed, this turns to 0. Thus the power dissipated as heat, assuming idealized torque characteristics, there is no eddy current loss. In that case, the power dissipated is given as the energy dissipated by rotor per minute divided by time. So this can be written from the previous equation as N times EH divided by 60, where EH is the hysteresis loss in one cycle and N is the relative motion between rotor and rotating magnetic field. Now at the time of starting, since rotor is stationary, thus N will be equal to Ns, synchronous speed, because the relative motion between rotor and stator rotating field will be Ns. The total input power goes to loss. The power that is being supplied to the motor will go to loss, since you don't have any mechanical output coming from that motor, and thus all the power that is being supplied will be lost in the form of hysteresis losses, assuming eddy current losses to be 0. So in this case, this power can be written as, from the previous expression, Ns multiplied by EH, since N becomes Ns, divided by 60. Ns multiplied by EH divided by 60. Now when the rotor runs at synchronous speed, then in this case hysteresis losses and induction losses become 0. There will be no relative motion between rotor and rotating stator field. Thus power developed will be given as speed times torque, which is given by the expression omega s multiplied by th, which is equal to 2 pi ns divided by 60 multiplied by th. Angular speed multiplied by the hysteresis torque, which is again equal to 2 pi multiplied by synchronous speed divided by 60 into hysteresis torque. Now from equation 2 and 3, they are equated. This yields hysteresis torque equal to hysteresis loss in one cycle of hysteresis loop divided by 2 pi, which indicates that hysteresis torque will be high if hysteresis loop is large. Now here is a home assignment problem. So the question is, a hysteresis motor has hysteresis loss in one cycle equal to 0.2 joules. The motor works at 50 Hz supply and has 8 poles. Calculate the hysteresis torque, power developed by motor, power loss at stall, power loss at synchronous speed. Now the advantage of such motor is that they are free from mechanical vibrations, thus making operation noiseless. The disadvantages are it has lower efficiency, low power factor, low torque. The application include the uses in precise speed drives such as servo mechanism, hard disk drives, clocks, sound recording, sound producing devices, and gyroscope teleprinters, etc.